Okay. 10.5. So last section in chapter 10, or at least the last section that we're going to cover. And this is just a summary of the rest of the stuff that's covered in chapter 10, or in 10.1 through 10.4. I'm actually going to talk about a few things that the book doesn't really go into in as much detail as I wish it would, but because I think it's really important for your conceptual understanding of what it is that we're doing. So I'm going to review some of the logic here with you again in 10.5, and then we'll just do some mixed review, which is really kind of what the book does in this section. It just does a bunch of mixed practice, which is important too, but I just want to take a second. Now that you've seen some hypothesis testing, it might make sense for us to go over the logic of it again, and it might make more sense to you this time around, okay? So we've talked about hypothesis tests for proportions, means, and standard deviations. In each case, the steps for performing the test are the same. You're going to state your null and alternative hypotheses. Then you're going to compute a test statistic. Once you have that test statistic, you can compute a p-value, which is a probability involving that test statistic in one way or another. However, if you're not doing this by hand, if you're using StatCrunch, which we did in every case, if you're just using StatCrunch to do it, then steps 2 and 3 are really done by StatCrunch at the same time. So really, you almost don't even have to worry about the test statistics so much. It's more the p-value. The p-value is what you're after. Once you have the p-value, then you can decide whether or not to reject the null hypothesis. And regardless of the kind of test you're running, you always make the same decision the same way. If the p-value is less than alpha, you reject the null hypothesis. If the p-value is not less than alpha, then you do not reject the null hypothesis. Once you have your decision, then you can write a conclusion. The conclusion is a statement about what that means for the alternative hypothesis. So if in step 4, you decide to reject the null, then that means there's evidence to support the alternative, and you would say so in step 5. If, on the other hand, in step 4, you decide not to reject the null hypothesis, then there's not evidence to support the alternative, and you would say so in step 5. Okay? So step 4 is a decision about what to do with the null hypothesis, and step 5 is about what that means for the alternative. To get the test statistic and the p-value for each of these things, if you're testing a hypothesis involving a proportion, you're going to go to stat proportion stats. If you're performing a hypothesis test involving the mean, then you're going to go to stat t-stats. And for the standard deviation, you're going to go to stat variance stats. When it comes to making this decision, again, if your p-value is less than alpha, you reject the null hypothesis. One way to remember this is that all of the positive statements go together and all of the negative statements go together. So if the p-value is less than alpha, then you do reject the null, and there is sufficient evidence to support the alternative. If, on the other hand, the p-value is not less than alpha, then you do not reject the null, and there's not sufficient evidence to support the alternative, right? So all of the negatives go together, all of the nots go together, okay? Now, why is that, right? Why is it that if the p-value is less than alpha, you reject the null hypothesis? Well, let's review a little bit about the logic here. If our sample yields a strange statistic when we assume that the null hypothesis is true, then our sample evidence is indicating that that assumption is probably false, so we reject it, right? So if we assume the null hypothesis is true, and then operating under that assumption, we get a sample statistic that is strange, that tells us that probably our assumption was false, so we reject it, okay? We determine if our statistic is strange by computing the probability that we would get that statistic, assuming H null is true. And that probability is the p-value, okay? So the p-value is the probability that we get the sample statistic that we observed if we assume that the null hypothesis is true. If we have a small p-value, then that means it's really strange. It means that it's strange for us to have gotten the sample statistic that we got under the assumption that the null hypothesis is true. And so it casts doubt on the assumption that the null hypothesis is true. So small p-value means probably the null hypothesis is not true. And so we reject it. All right, so if our p-value is small, then our statistic is strange. So we reject our initial assumption that H naught is true. Now, how small is small enough? Well, smaller than alpha, right? Smaller than alpha. But why alpha? Well, you may recall that alpha is related to our level of confidence. If our level of confidence is 95%, then alpha is 0.05. So loosely speaking, right, very loosely speaking, if we want to be 95% confident, then our p-value needs to be less than 0.05. If we want to be 99% confident, then our p-value needs to be less than 0.01. If we're okay with only being 90% confident, then our p-value only needs to be less than 0.10, right, and so forth. In general, if we want to be 1 minus alpha times 100% confident, then we need the p-value to be less than alpha. And that's why we reject the null hypothesis only if our p-value is less than alpha. Okay, so as I said, hopefully now that we've seen several, now that we've been through several hypothesis tests from beginning to end, hopefully this logic makes a little bit more sense to you. If it's still not making a ton of sense to you, grab yourself a yummy bowl of ice cream and a comfy armchair and ponder. You've got to understand this. And there's only so much I can say to help you, right? Ultimately, it comes down to you sitting down and putting forth the mental energy that you need in order to understand this information. It is important to me that you understand this, okay? So make sure that you've got the logic here. Now, I wish that the textbook would ask you questions like this one. Actually, come to think of it, I think they do. I think there are a couple homework problems that ask you questions like this. But I wish they would ask you more questions like this, because this really drives home what it is that the p-value is measuring, okay? And I'll tell you right now, I'm going to ask you questions like this on your test, okay? So make sure that you understand the solution here. So this one says, suppose that you want to test p equals 0.41 against p less than 0.41. You collect a sample that has a sample proportion of 0.38. Well, that is less than 0.41, right? But is it different enough? Well, to test that, you run the appropriate hypothesis tests, and you end up with a p-value of 0.2143. What is the meaning of that p-value? Okay, I'm not asking you to run the test. I'm not asking you to make a decision, write a conclusion. I'm just asking you, what does this mean? What does it mean? That your p-value is 0.2143, what does that mean? I'm saying give both the mathematical equation and explain it in words. So let's do that. What does this mean that our p-value is 0.2143? Well, if you've been listening to the lectures, I explain what the p-value means in just about every hypothesis test that we run. So hopefully you can kind of do this on your own. But I'm going to lead you through this one. So here's what this means. This p-value is the probability that we would get this sample statistic if, in fact, the null hypothesis were true. In other words, if we assume that p is 0.41, then the probability that we would get a p hat value of 0.38 is 0.2143. In other words, there's a 21.43% chance that we would get a sample proportion of 0.38 if our population proportion is 0.41. So you can write down any version of that you like best. I think I'm going to go with the last one. I'm going to say there is a 21.43% chance that we would get a sample proportion of 0.38 if, in fact, the true population proportion is p equals 0.41. Okay, so that's the explanation in words for what the p-value is. That this is what the p-value means. And if you're thinking about what decision we would make here, well, we would not reject the null hypothesis. Our p-value is not small enough, right? We have a p-value of 0.2143. The smallest alpha usually ever is like 0.10, and this is not less than that. So we would not be rejecting the null hypothesis. But hopefully you can see why now. It's because there's such a large chance that we would get this sample statistic under the assumption that the null hypothesis is true, that it does not cast doubt whatsoever on the truth value of the null hypothesis, right? So we don't reject the null, okay? If you understand what the p-value is, it'll be much easier to remember when you should and should not reject the null hypothesis. Anyway, that's the meaning of the p-value in words. Here's the mathematical equation that expresses that same thing. It's much shorter. We would say the probability that p hat is 0.38 or more extreme. So in this case, since we have a left-tailed test, we would say the probability that p hat is 0.38 or less, right? So less than or equal to 0.38. So the probability that p hat is less than or equal to 0.38, given that the true proportion is 0.41, is 0.2143. Okay, so that's the mathematical equation that expresses that same idea. So aren't these symbols beautiful? Once you know what they mean, it makes it so much easier to express certain ideas, right? So that's that one. Let's look at another one kind of similar to that. So example 2 is pretty similar. So it says, suppose that you want to test mu equals 75 against mu greater than 75. You collect a sample that has a sample mean of 78. You run the appropriate hypothesis test and get a p-value of 0.1043. What is the meaning of that p-value? That should say what is the meaning of that p-value? Go ahead and pause the video. See if you can do this one on your own. Okay, so here's my solution. So I'm going to say the meaning of this p-value. So there's about a 10% chance, there's a 10.43% chance that we would get a sample mean of 78 if in fact the true population mean were 75. Okay, there's some drama happening with my children. This is just, you know, you guys have been hearing a lot of noise in the background lately. This is just a typical average day for me. I almost drown it out. Like I almost don't even hear it anymore. Anyway, okay, but let's write that down. So the meaning of this p-value, we would say, I'm going to word it a little differently than I worded the first one, just because I want to give you a different way to think about it, I suppose. But I would say something like this: assuming that the true population mean is 75, the probability, or maybe I'll say there's a 10.43% chance that we would obtain a sample mean of x bar equals 78. right? So assuming that the true population mean is 75, there's a 10.43% chance that we would obtain a sample mean of 78. So is that good enough to cast doubt on the assumption that the true population mean is 75? Well, not really, right? That's not very odd. Even if alpha was as big as it usually gets, which is 10%, this is still not less than 10%, right? So we wouldn't be rejecting the null hypothesis here, but it's because it's still a fairly likely thing to happen, right? If we assume the true mean is 75, there's a pretty good likelihood that we're going to get a sample mean of 78. So we're not going to reject this assumption, right? In math symbols, we would say this: probability that x bar. Now in this case, we're computing the probability x bar is 78 or bigger, right? Or bigger. So probability x bar is greater than or equal to 78, given that mu equals 75, is 0.1043. Okay, and that's that. So hopefully that gives you a little better understanding of what the p-value is. If not, again, you need to sit down and force yourself to understand this, right? You need to sit down and make yourself understand what's going on here. So you can rewind and rewatch and re-listen to my explanations. If you're still not getting it, I mean, send me an email, you know? But it's very important to me that you understand this. Okay. So now let's actually run some hypothesis tests from beginning to end. What this section is really good for is giving us mixed practice. It's like when we were in 10.2, we knew that every problem we saw, we were going to be testing proportions. In 10.3, we knew that every problem we were going to be testing means, right, and so forth. But on a test or a quiz, you're going to be confronted with just a random problem, and you're going to have to know, using the context clues from the problem itself, what parameter you're testing. So this section is really good to give, it gives us some really good mixed practice to get good at that. So let's look. In October 1945, the Gallup organization asked 1,487 randomly sampled Americans, do you think we can develop a way to protect ourselves from atomic bombs in case other countries try to use them against us? 788 responded yes. Did a majority of Americans feel the United States could develop a way to protect itself from atomic bombs in 1945? Use blah, blah, blah. So we have to figure out what parameter we're testing first and foremost. They ask us in that very last question, right? Did a majority feel blah, blah, blah? Did a majority feel a certain way? Well, how do you measure that? You measure a majority. What does majority mean? Well, majority means more than half, right? It means more than 50%. In other words, it means that the proportion would be more than 0.5. The proportion of Americans who felt that particular way would be more than 0.5, right? That's what majority means. So that's our alternative hypothesis right there, and that tells us what the parameter is. We're testing proportions here, right? So we're going to be testing that the proportion is greater than 0.5. That's what we want to see. That's what we want to determine if it's true, right? If p is greater than 0.5. So then the null hypothesis is, of course, that it's not true, right? That it's not a majority, that it's just equal to 0.45 or 0.05 or possibly less. Okay. Now, what sample information do we have to help us make this decision? Well, we were told that 788 people out of the 1,487 people sampled felt the way that we're being asked about, right? They felt that we could develop a way to protect ourselves from atomic bombs, right? So that's our sample proportion, 788 out of 1487, right? So p hat is 788 out of 1487, and it's not totally necessary to come up with this value, but I like doing it just to give me some intuition going into StatCrunch. So 788 out of 1487 is about, if I round to 3 decimal places, this is 0.530. So about 53% of people. That is more than half, okay? But is it different enough from 50% for us to safely say that a majority felt that we could develop a way to protect ourselves from atomic bombs? Well, to answer that question, we're going to run the test, right? Since we're testing proportions, we're going to go to stat, proportion stats. We only have one sample, and we don't have the data. We have a summary. When we go there, we'll be prompted for the number of successes, which we said a second ago was 788, and we'll be prompted for the number of observations, which we said a second ago was 1,487. And that should do it. We should be able to, I think that's enough information for StatCrunch to give us the answer. So let's open up StatCrunch. We're going to go to stat, proportion stats, one sample with summary. 788 successes out of 1487 observations. We want to test if P is equal to 0.5 against P greater than 0.5. So we hit compute. There's our sample proportion again, which we figured out on our calculator. But more importantly, there's the p-value, right? So our p-value is 0.0105. 0.0105. So what does that mean? Well, that means that there's a little over a 1% chance that we would have gotten this sample proportion if the null hypothesis were true. 1% isn't very much. It's less than the 0.05 level of significance that we were asked to use. So we're going to be rejecting the null hypothesis here. We're going to say, yeah, this is actually kind of a strange thing to get 53% if the real population proportion were only 50%. So definitely, yeah. We're going to say since 0.0105 is less than alpha, we reject the null hypothesis, okay? And remember, all of these positive statements go together, right? So the p-value is less than alpha, so we do reject the null hypothesis. That means there is sufficient evidence to support the alternative. And what's the alternative? The alternative is that the majority felt this way. So we're going to say, in conclusion, that at the 0.05 level of significance, the evidence suggests that the majority of Americans felt that the U.S. could develop a way to protect itself from the atomic bomb. Okay, duck and cover, right? But that's that. Okay, so there's that one. Let's do just a couple more. Okay, so just a couple more examples. So this one says, a pharmaceutical company manufactures a 200 milligram pain reliever. Company specifications require that the standard deviation of the amount of active ingredient must not exceed 5 milligrams. The quality control manager selects a random sample of 30 tablets from a certain batch and finds that the sample standard deviation is 7.3 milligrams. So that's not good, right? Assume that the amount of active ingredient is normally distributed and determine whether the standard deviation of the amount of active ingredient is greater than 5 milligrams at the 0.05 level of significance. Okay. What did we just read? No, it says determine whether the standard deviation is greater than 5 milligrams. So we want to determine if the standard deviation is greater than 5. The null hypothesis then is that the standard deviation is equal to 5. What evidence do we have to support the alternative hypothesis, the claim in the alternative hypothesis? Well, the sample information that we have is that the sample standard deviation is 7.3. That is larger than 5. It's quite a bit larger, actually. I would be surprised if we did not reject the null hypothesis. I think we probably will reject the null hypothesis here. I could be wrong, though. The only way to be sure is to run the test. So here we're testing standard deviations. And by the way, you have to use the correct symbol. I've been telling you since the beginning of the semester to memorize these symbols. And if you haven't done so already, well, now the crap is hitting the fan, right? You have to use the correct symbol. Here I'm using sigma because we're testing standard deviations. On the previous problem, I used p because we were testing proportions there, right? So you have to use the correct symbol. Anyway, so we're testing standard deviations. Let's do it. So to test the standard deviation, we go to stat, variance stats, one sample, with summary. When we go there, they'll prompt us for the sample size. In this case, it says that the quality control manager selects a random sample of 30 tablets, right? So our sample size is 30. And then they're going to prompt us for the sample variance. Remember, the standard deviation is 7.3, so that means the variance is 7.3 squared. So that's what I'm going to enter into StatCrunch. Let's see what we get. So I'm going to stat, variance stats, one sample with summary. Sample variance was 7.3 squared. Again, to get that caret symbol, that's above the 6 on your keyboard. So hit Shift 6 to get the caret symbol. Alternatively, you could just enter 7.3 squared into your calculator, and whatever number it gives you, put that number in here. But anyway, 7.3 squared, the sample size is 30. We want to test to see if, now when we wrote down our hypothesis test, we said the null hypothesis was that sigma equals 5. Here they're stating that the hypotheses in terms of sigma squared. So if the null hypothesis is that sigma equals 5, that means sigma squared would be 5 squared, or 25, right? If you know that 5 squared is 25, you could just enter 25. The alternative hypothesis was right-tailed in this problem, so change that, and then hit compute. And yeah, sure enough, right? We get a really tiny p-value, 0.0004. Okay, so our p-value equals 0.0004. In other words, there's less than a 1% chance. There's like a 0.04% chance that we would get this sample standard deviation if in fact the true population standard deviation were 5. So that means we're going to be rejecting the null hypothesis for sure, right? Since 0.0004 is less than 0.05, we reject the null hypothesis. What does that mean? Well, that means that at the 0.05 level of significance, the evidence indicates that the alternative hypothesis is true, right? What is the alternative hypothesis? The alternative hypothesis is that the amount of active ingredient, or the standard deviation in the amount of active ingredient, is more than 5 milligrams, right? So the evidence indicates that the standard deviation of active ingredient in this pain reliever is more than 5 milligrams. Okay, so it's more than 5 milligrams. That's bad news for this particular pharmaceutical company, because that means that their standard deviation is exceeding their company specifications. And that's also bad news for anybody taking this pain reliever, because, so again, if you think about what the standard deviation measures. The standard deviation measures how much variability there is. So when we say that you have a large standard deviation in a pain reliever, then that means that one pill doesn't have very much active ingredient and another pill has a lot of active ingredient. And that's potentially dangerous, right? Because that means that you could overdose if you just so happen to be unlucky enough to get a bunch of those pills that have more active ingredient in them than they should. That's why it would be bad for a particular pharmaceutical to have to have a large variability in its active ingredient, right? So this is really bad news for this company. They probably deserve to go out of business, right? Anyway, but that's that one. Let's do one more. So it says, among individuals who had credit cards in 2010, the mean number of credit cards was 3.5, according to the Federal Reserve Bank of Boston. A random sample of 160 credit card holders has a mean of 3.3 cards and a standard deviation of 2.3 cards. Do these results imply that the mean number of cards per individual is now less than 3.5? Use the 0.05 level of significance. Okay, so first thing we need to figure out is what parameter are we testing? And that was given away in several places throughout this problem. Like right off the bat, the very first sentence says among blah, 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 the mean number of credit cards. And then later on it says random sample of blah, blah, blah has a mean of 3.3 cards. But then most tellingly of all, the last question there, do these results imply that the mean number of cards per individual is now less than 3.5? That gives you your alternative hypothesis right there, right? We want to know if the mean is less than 3.5. Notice again, I'm using a different symbol. We're testing means, so I'm going to use mu for that symbol. So the null hypothesis then would be that mu equals 3.5. What sample evidence do I have to support this claim? Well, the sample mean was 3.3, right? That is certainly less than 3.5. Is it different enough for us to cast doubt on our assumption? Well, we have to run the test to make sure. This is kind of a close call. Here, I would be surprised if we reject the null hypothesis. I think probably we're not going to reject the null hypothesis. But we'll see. I mean, we have a pretty solid sample size, 160. So maybe we will reject the null. Let's see. We go to stat. If you're testing the mean, you go to t-stats. One sample with summary will be prompted for the sample mean, will be prompted for the sample standard deviation, and will be prompted for the sample size. 160, right? A random sample of 160 credit card holders. So let's go to StatCrunch and see what we get. So we go stat, t-stats, one sample with summary. Sample means 3.3. 3.3. Sample standard deviations, 2.3. And the sample size is 160. Notice that they're prompting us for the sample standard deviation here, not for the sample variance. So you don't need to square this value, right? They're just asking for the sample standard deviation, not the sample variance. Okay, And then we're testing mu equals 3.5 against mu less than 3.5. Okay, so there's our p-value, 0.1365. Not quite good enough to reject the null hypothesis, right? So let's write that down, 0.1365. In other words, if we assume that the true mean is 3.5, then there's still a 13.65% chance that we would get a sample mean of 3.3. That's fairly likely. So it doesn't cast any doubt whatsoever on this assumption. So we're not going to reject it, right? More formally, we would say this. Since 0.1365 is not less than our level of significance, 0.05, we do not reject the null hypothesis, right? So remember, all the positive statements to go together, all the negative statements go together. So here the p-value is not less than alpha, so we do not reject the null hypothesis. That means there's not enough evidence to support the alternative. So let's say that in our conclusion. So at the 0.05 level of significance, there is not sufficient evidence to support the claim that the alternative hypothesis is true, that the mean is less than 3.5. That the mean what? That the mean number of cards per individual is now less than 3.5. Mean number of credit cards per individual is now less than 3.5. Okay, and that's that one. Oh, sorry, I should have expanded that so you could see it a little better. Anyway, that's that. Hope that helps. I'll check in with you again soon.